Okay, so a couple of things that we want to do in this next section here is we want to define an age property per point. This is the property we're going to be using to grow across the surface and control the spread of the disintegration, both in terms of the pattern and the speed of it and all those types of things. The other thing we want to do is control the scale of each face. So remember, we are going to be, we've detached the faces from the mesh and we want them to shrink down to nothing. That's the other thing we want to do. So we can use that age property not just to control kind of what part of the mesh is getting disintegrated and how and the pattern of that and all that kind of stuff, but also to control the actual shrinking of the faces. So this is of course a custom point per point property similar to the ones we've already made, but we're doing it directly on the face point object that we created here. So so the first part is just to set up this geo property. So we want to do set geo property. We're just going to call it point age. Now in other, if you go Google around on the internet, you can see people doing these kinds of disintegration effects using various softwares, and some of them have done similar videos, and you might see, concepts like infection or, because you could think of this as kind of something that's infecting something, or growers, or grow, or different words like that. But I just think that in the end, this is all about kind of using time to let something spread, and it feels appropriate that age and time is how we think about what we're doing. So. Again, if you prefer to think of this as an infection spreading type of thing, you could call this point infection or whatever. But anyway, so yeah, so we want to set up that little geo property on our sim points, or face, really on our face points here that we're creating. So I'm going to turn off this for a second. We're just going to be focusing on the points for most of this section here. So turn the point display back on. So here are our points. We've set up an age, but what we haven't done here though is we've defined the age property, but we haven't given it data. So it needs to have some kind of initial data. So a couple of ways to do this, but I think that for something like this, it's nice to be able to provide a mesh and say, hey, all of the points within this mesh, say a convex mesh to make it simple, are going to get initialized with some age value, and then we're going to spread the age growing from there. So let's do it that way. So first we'll make us a small mesh here. I'll make another sphere. There we go. Move it over here. Yeah. So turn on wireframe. Yeah. So that should tag. Basically, want to use a sphere to tag some initial set of points and activate them, make their age non-zero, and then spread the age property across the points. So yeah, let's start off with that. So we'll use this new sphere, bring that into the graph, and then what we want to do is a simple kind of, again, this is the kind of compound that, it should probably become available in some kind of compound pack in the near future, but right now we don't have that available anywhere. I don't even think we have anything like this in the Rebel pack, so we're just going to hand roll it ourselves, but it's basically going to be a points inside convex polygon, a simple implementation of that. So I'll just make a compound out of this. So what we really want to do is basically this thing is going to take a mesh and then take points coming into it. So let's start with the points. So basically we're going to have these points going in, and we're going to bring in the mesh sphere here, and we're going to basically spit out the indices of all of the points that are inside this mesh, assuming this mesh is a convex polygon. So let's call it points, or point indices in convex mesh. And by requiring it to be convex mesh, it just makes it easier for us to compute this, to make this compound work well. So the basic idea will be that what we're going to do is get the point positions of the points, and then get the closest points on the surface, so get closest locations. Actually, what we want is get closest point, I think. not the equations. So what we want to do is get the closest point here. So given these positions, given the positions of our point cloud, find the closest position on the sphere. So get it on that sphere. We're not going to use a cutoff for now. We're just going to get the closest point. So we're going to sample the normal. So sample property. So what we want to do is get the normals on the mesh and essentially check if the dot product between that normal point. So in other words, if the normal is pointing in the same direction as the vector from the point to the closest surface, then we're inside. That's basically the check. And so let's get the normal at the closest point. So plug in the location on the mesh. We're looking for point normal. And it's going to be level 3. So there we go. And then that's the normal. We also want to sample the position, sample property. And we want to sample point position, which is a float 3. So likewise, that closest position on the mesh, from the mesh. Okay. All right, so that's those guys. And so we want to do the dot product between the normal with the vector going from the point to the thing. So that would be, so actually adding, subtracting, so subtract the destination minus the origin, I believe. So let's see that. Yeah, I believe that's right. And then we'll use, that's the dot product. So if it's, basically the dot product is positive, then they're pointing in the same direction. So that means greater or equal to 0. So that's going to be true. And then what we can do is we can say find all in array. So this is a quick way, like whenever you generate an array of booleans, or really any array of anything, if you want to just get the indices in that array that represent certain values, you can just do find all in array. So the array is this array of bool, find all the elements where bool is true, and give us the index list of those, and that's it. So we should be able to now, let's see here, do this. So we're gonna set in array some age value, right? So we're gonna say it's okay. Let's set the age value to be 1 just for now, just to make this simple. So we want the value to be 1, and we're gonna set it in the array of the initial age values. Now we don't even have that array, so we need to make that array. So I'm just gonna do a sequence array, and make sure all the ages are 0 and the step is 0. So basically everything, we're just going to make an array of zeros here that's not increasing, so step is 0. And we want it to be equal to the same number of points, or the length of this array should be equal to the number of points in the point cloud. So we'll just get point count. So here we go. And that's it. So we have generated an array of zeros, but in that array we're going to set values of 1 for the indices corresponding to points that are inside a convex mesh, which happens to be this sphere in this case. And that is going to be our initial age values that we plug into data here for the point age. So that's all done. Now, a quick way to check if this is even working or doing anything is we can just use this point scope and go to this section here, color. We want to color by property, basically. So let's put in point age, and actually we might, or a simple one too would be to just do take the magnitude. But anyway, it doesn't matter. So we can see anyway that we're good. See, we're coloring our points, the point scope is coloring our points by the point H attribute or property, and we're getting and we can see here that it's just setting the points within the sphere to be one, value of 1. If I were to, just to double check, if I were to say change, expand this, we can see we're setting more of them. If I were to move this guy around, we'd be setting the age to 1 in a different place. So that all seems to be good. So yeah, so we got, let me rearrange a little bit here. So we have managed to roll our own point indices in the convex mesh, pretty good. And this is basically our initializing the age value. So what we can do, I think, here is select all these guys here and make a single compound by Control G-ing them. And I'm just going to call this initialize age, point age. And I'm going to call this points and out points just to make this even easier. So we're constructing our points here, and then we're initializing point age using an external, I'll call this convex start region or mesh. So that's the part where we start. Okay, cool. So that's that, and the solver should still work. So if we hit play, we should still see them move, and we do. So everything, nothing weird is happening. So next step here is going to be to go ahead and make these guys grow. We want to spread those age values from that starting position. So let's do that next. All right, so to spread a property across a point cloud like this in general, we're going to use some of the new functions and capabilities of Bifrost 2.1.0.0. The chief one is get points in radius, this one. So what this is going to allow us to do is that, given any point in space, I can just rapidly get a collection of other points in the point cloud that are within the radius, the provided radius here of my point. So what I'm going to do is build a lookup table so I can rapidly access this list later on during the simulation when we're growing or spreading that point property across the point cloud. So without further ado, let's also try to understand how we can visualize how this thing works using the location scope, which is also a new scope, which allows us to visualize closest point lookups and raycasts and all kinds of stuff. It's really cool. So we've got our point sim here. So let's start by figuring out what kind of radius we should use and understanding how this works. So I'm going to plug in the geometry here. We're going to get points in radius. Let's just get the points that are tagged as active as our visualizer here. So I'm going to go back in here and spit out, I'm just going to do get point positions here, and then get from array. So get those point positions from this array here. And this is just kind of temporary. I'm just going to do this to help visualize some things here. So those are our positions. We want to get the closest points in the radius of those guys. And we'll just kind of keep the radius at 1 for now. Plug those locations in to the location scope, which will help us visualize this stuff. And the geometry is our points. And the positions is over here, they're over there. And then put an output. So here we can see right now with the radius of 1, they're picking up quite a few, pretty big area. So maybe we don't want to use 1, let's just use like 1.5. That's pretty good. So that means that, for example, this point here is picking up, a couple of different neighbors. So, so this is something we can play with. We can also enable a max number. so we don't pick up too many. I've found just in this case, higher numbers are pretty good, like 24 to 32. So we'll just use 32 as our kind of max number. Yeah, anyway, so what we really want to do now, this compound is pretty optimized and it's pretty fast, but it does involve building lookup tables and all kinds of stuff every time you call it. So you obviously don't want to be doing it inside of an inner loop. However, we do want to be using this lookup table or the closest point information during the growth solver when we're growing the attribute. So we do want it to be fast. So one way is to just do this once, because we know that the relative, so if we think about this grid and we're spreading it across the surface, even if the points are moving around on the original mesh, the relative connectivity between these points isn't really going to change. We want it to grow in the space, the undeformed rest pose space. That's really the space we want this thing to grow in. And that means that we can actually compute this closest point thing once and stash it away and just refer to it during the simulation. So we're going to take advantage of the fact that we do want this to happen in rest space, or rest, basically the rest space of the points. So all we're really going to do is stash away the point indices here. So I'm going to do a set property. Now I'm not going to do a set geo property, because geo properties store data per point or per voxel or per face or whatever. This is just going to be just a chunk of data I'm going to stash away on my object, on the point object. And so that's why I use set property and not set geo property, because it's not data per point. The point indices here is an array of an array. So it basically means that the first level of the array is for every point in the point cloud, every point in these positions that we feed it. And then the second level would be the closest points for that point. So that's why we have a double array. So that's the value. So I'm gonna call this closest points, basically. And we're gonna do that. Actually, we really want to be doing this before we run our sim, because we're going to use it in the sim. So at this point, I think we've seen the visualization. We can kind of stop that for now. That was just a way to help us see how this thing works. So now I'm gonna rewire this a bit. So what we really want to do is stash away the closest point kind of cache on our object. So I'm going to put that here. So get the closest point in the radius, and we actually now what we want to do is we don't even want that anymore. We can get rid of this, because that again was just to help us visualize how that get closest point worked. And now we know that, so we can delete all this stuff. All right, so what we want to do now is say, okay, for every point in the point cloud, get the closest points for that point. So I'm going to do get point position. And plug that in and plug it in the geometry. So we're saying get all the points in our point cloud, get their positions, and find their closest points on that point cloud within some radius, which is 0.5 right now. And don't pick more than 32 closest points. And then those indices are now stored as this property, not a geo property, but a regular property called closest points, which we can later look up, and that cache is now living on our point cloud object, and that's what we're going to feed to this thing here. And so that's step one. Then in here, before we do the simulation of the point positions, we should go ahead and update this age value here. So I'm going to make a new compound here called update age, or spread. How about spread? Grow age. Grow point age. That's what we're doing. So let's do that. And so the first thing we'll do is get that property back. So get the property. And I forgot exactly what we called it. I think it was closest point. Yeah, closest points with an S. So I'll go back in there and call it get closest points. And I believe it was an array of an array. It's complicated enough. We're going to have to go to our little menu here and go to integer. I think it was an unsigned int array of an array. So it makes a 2D array here. I believe that was what it was. I will double check again, just in case I get it wrong. Yeah, no, it's an array of long. Look at that. You can see it down there. It's long. So not unsigned int. So let's change that. So it was just a regular, good old long array, 2D array. So array of long. All right, that's it. So we're getting those closest points. Now, so again, we have an array of an array. So we're going to do a for each in parallel here. And then we want to basically find out what the contribution, so for every point in the point cloud, find the contribution of its surrounding points to that point. So we're going to plug that in. Now, in this case, we really just want to iterate over the top level array of this array of arrays. In a situation like that, where we don't need to do anything fancy, we can just get rid of the max iterations by deleting that port. And then, very importantly, setting this value to be iteration target true. By configuring in my loop this way, I don't need that max iterations anymore. And I can just say, hey, this is the iteration target. That means run this for each in parallel on every single value in this array. And of course, every single value in this array is another array. And that's why on the inside of my for each, I'm still getting an array, because now in here, I'm seeing the list of indices that are the closest to the current point being considered by the loop. There it is. And I should probably call this something other than values. I'll call this closest in the index. So this is going to be all the closest indices of the neighboring points given the current point being iterated on. So all I want to do is find the contribution. So I'm going to do a sum array. So, oh yeah, and I can't sum the indices. That doesn't make sense. What I need to do is, of course, get their age values. So let's do a get geo property on the point age. So point age. So that's what I want to be getting the age here. So array of float. And this would be the point age. I'll call this point age to be clear. That's what we're getting here. So we actually want to be summing the age, but we can't just plug this in because we need to be picking only the indices of it, the indices of the closest point and get their age, right? So we have to do get from array. So basically, given the closest indices, look up the point age for those indices, and that's what we're summing. And that gives us the sum of all of the age values. So this would be the point age sum. All right, so this is good. Now we have an array, and so every element in this array basically represents the sum of all the age values that are close to this thing. What we could do, we could make this a weighted contribution as well by taking the distance. So we could also be getting the get closest position, get point position here, plug that in and get that from the array, and then subtract that from the current position and that kind of stuff to get the weighted, kind of a weighted contribution as opposed to just a straight sum. But that's fine. Maybe we'll just do the average value for now anyway. So if we want to do the average, we have to divide this by the number of vertices or closest points, which is the length of this array. So I'll do array size. That's going to be a long, and long converted to a floating point value will become a double, which will then propagate a double here, and we don't want to mess with doubles. So I'm going to just turn this into an integer, or actually even better, just a float straight away. So 2 floats there. That way I prevent Bifrost from turning that into a double. So I'm taking the sum of the array divided by the number of elements as represented as floats, and that gives me the so you know what, we're just going to do that. We don't really need this. We just want the weighted. We want the point age average. This is the average point age in the neighborhood. Great. That's it. So now every point, so that basically means that this point over here, for example, is going to be picking up these three guys. It'll also pick up all these other black guys. But what will happen is that these three values are going to influence its value. So this point age average will be greater than 0 because of these three guys. If it picks up these, it will be even bigger. And that means that this guy should get colored, or should get, its age should increase a little bit because of this. So what we can do is just add, so what we're going to do is take this here and add that to the actual point age. And that means that for the guys over here in their neighborhood, it's all going to be 0. So we'll just be adding 0 to 0, and they remain dark. But the points over here that are close to the light points, they're going to start getting some age getting added to them, if that makes sense. And that's what we're doing. And then we're going to set point age, or actually, sorry, set the geo property. And the geo property we're setting back is point age, because we have now calculated new values for point age, and we now need to update the new point age. So that's what we're doing, using those new values that we computed. Point age, very good. And that's it. That is the basic way to grow point age. No problem with that. And by also hooking up this inside of our simulation, we are taking advantage of the fact that we're already keeping track of the state of the points. So we don't need to do anything more with feedbacks. We can just use the existing feedback infrastructure we have going here already, so that the age grows from time step to time step, right? Because we've added the point age to our object, to the point object, that state that includes the age now is part of the feedback, right? So anyway, so if we now look at this, we should see it grow. All right, we do not see it grow. What happened? Let's see. Am I okay? So we got that initial growth. We're stashing closest points, and we are simming. Let's see. I don't see them at all changing color. So let's see here. Okay, so let's quickly debug and see what's happening. For example, am I getting an array here, 400? Yes. So it's definitely finding the closest points, finding 400 of them apparently. And in here, what kind of values are we getting out of here? 0 to 0.4. So it should be adding like 0.4 or so to them. And so we're getting the point age here. Is there something wrong with that? Nope. That looks good. And we're setting point age back. So let's see here. Although, yeah, something is wrong, because what's happening is that this should be increasing, right? We should be able to see this max value get bigger and bigger, because as we keep adding, actually not necessarily. Okay, I realize now what I did wrong. So the problem, there's nothing wrong with all this stuff we just did. This is all correct. The problem is the fact that, of course, I didn't modify the wiring here at the top level, where after we grow our age, we then get the point position to do the noise movement, the motion of the particles. But then when we're setting that final position, we're setting it from the switch on start frame data, which is before the grow point age. So all the growing we did here is lost, because that's carried through here, and then that is removed here because we've just isolated the position part, and so we're connecting back here. So anyway, so what I need to do is connect from here. So basically what I need to do is say, hey, let's get the data from the right frame, and then let's grow the point age. And once we've grown the point age, then set the new positions, preserving that point age. And if we do that, then of course we're good. And we have now spread the we spread everything. And it's kind of cool because you can even see on the first frame how the values are spreading here, as you would expect. You can see if I step through how it spreads across. So we have a basic spread, and I think at this point we might want to increase the resolution of our sphere, because we're going to start getting more and more fancy with this now, and that resolution is just not good enough. So let's go and increase the res on this guy. Let's see here, where do we do that? Polysphere, here we go. Let's go to 100 by 100. Yeah, that's too much. How about 60 by 60? That's better. And I think we can hide that sphere again now. And the other thing we can do, I'm going to hide the other sphere. I think the sizes of these points are a bit big fat, so I'm going to make them smaller. There. So now we can see a bit more. And notice also how, again, since we're spreading this in rest space, which is the undeformed original space, even no matter how our points get moved around by a velocity field, or in this case noise, our ability to spread it across the original topology is what we're after, and that's what we're getting here. And that's again because we're stashing away that original point in radius as part of our initial setup here before we start simulating. All right, so next up, let's introduce some non-linearity, or rather, actually, let's introduce some kind of fracture lines happening here. We don't want to just be spreading evenly from that first region. We really want to start having some kind of fracture type pattern happening. And then after that, we will start driving the size of the face, the faces that we're breaking away from the mesh. Let's drive their size with these age values so we can start kind of shrinking them. And we'll start realizing how this all is going to come together to actually make that effect in the end. Okay, so to add some, to break up this even pattern, or lack of pattern rather, we're going to go into initialize point age. And actually we're going to, before we do that, we're going to initialize, we're going to create a new geo property, point property, called point noise, quite simply. So let's do that, set geo property. And we're going to call it point noise. So this will be this is basically just going to be a noise data, a noise function, if you will, that we're going to sample across all the points and use that to guide the propagation. So before we initialize age, I'm going to create this noise, and we'll do something similar. We're going to get the point count. So we want to actually, all we really want to do is get the point positions. So let's get all the positions of our points, and then we're going to look up our noise function. I think I'm going to just make it a little compound immediately here, because it's not going to fit easily. So there, we'll just call this initialize point noise. So go in there. All right, so here we go. So we have our point position. Let's just use fractal noise for this. So plug that in there, and we'll just use the default settings right now. And so we're going to get fractal noise per point, and that's what we're going to store as data. Here we go. So we're going to get every position, sample a fractal noise function at that point position, and then store the result of all that as a point noise property, point property. And that's all we're doing, and at least for now. So how is this going to help us? Well, before we even know that, we need to just visualize. We need to see this noise. So I'm going to put down, actually we already have a point scope over here. So I am going to just disconnect this for a second and use the point scope on this guy here. So let's see what this looks like. So now we see our black points, but what we want to visualize now is not point age, but our new point noise. So here we go. Ooh, look at that. We can see our noise values. And as you can see, it's not very detailed. That of course means the frequency is way too big. We need too low, too small. So we need to increase this frequency. Let's go to 0.1. That's a little bit better. How about 0.5? Yeah, I'm starting to get there. Starting to see some nice noise patterns. 1. Yeah, pretty good. Maybe even higher. 2. Yeah, that's probably about right. And again, I think we just need to increase the resolution of the sphere itself to capture some of this detail we can get here. So let's go to 80 by 80. How about 100 by 100? Let's get 100, 100. There, that's pretty good. Yeah, so now we can clearly see these kinds of patterns here. Now what I've found is that what we really want to do is create these tendrils along which our face will break up. And right now noise values, as we can see, if I put a watch point here, we're getting both negative and positive noise values that seem to be roughly normalized. They go a little bit above and below -1 and 1, but not much. So they're kind of in that range. So I've found that just aesthetically for what we're trying to do, it looks better if we take the absolute value of our noise and use that for the noise. And that's partly to eliminate the negative values because it makes our math simpler later. But it's also just to get a slightly better look. So let's see. We're also going to want to use these low values as our guide, right? So if we have these negative ranges here, we can use these low noise values to say here is where we want the propagation to happen. So, all right, so we've got our noise set up. So the first thing we'll do now is when we initialize age, we're going to sample this new point noise. So, so we create the point noise geo property here, and then inside a point age, we can look it up and use it in our sampling. So let's get the geo property point noise, and that's a array of floats. So we'll get that from there, and now so this data is going to be the noise values. So what we can do now is, instead of just setting the value to 1, if the points are inside that control sphere we have that initializes our point age, instead of literally just setting the value to 1, what we can do is just set it to be the noise values instead, or at least have that guide our initial values. So we can't just plug this in because this array is the array of all the points, and we're just setting the indices that are inside that convex mesh. So we have to do a get from array. So basically use the indices that we're actually setting, so use those indices, and then use them to look up the noise values in our array. And those are the values we want to set here. So that's what we're going to do. So let's take a look now. We don't need to look at the noise values anymore. We can just plug the scope back where it used to be, which was after the sim, or actually it was, yeah, after the sim points here. And then what we're going to do is look at point age once more, because we're back to looking at that. And we can now see that, you know, our little sphere here is still controlling the starting region, but now that we're sampling that noise, we're initializing point age with noisy values instead of this, you know, thing. So if we now hit play, we'll see that it'll spread from there. Of course, the spread is still very smooth, but at least we're starting to see some variation in that first pass. So before we go any further, we do also want to take into account the aging rate that we defined, not just for the actual aging, but also for the initial age. So that means that we need to have, you know, an input here and here. So what I'm going to do is put down a value node that can act as sort of a global control for the aging rate so that I can wire to multiple nodes. So we'll make the global default 0.1 for that. Now, normally in Bifrost, the nodes, like value nodes, will show the value here. But in this case, I think it's better that we, show that this is actually the control for aging rate. So I'm going to change the name display mode from value to name on this, and then we can type in aging rate, and then can be 0.1. But that just makes it more clear to read, I think. The other scenario would have been we could have created a backdrop as well, and called it aging rate, aging rate, and then put the node in there and show the value. Just depends on what you want to do, but I'm going to do it this way. So let's put the aging rate in here, and I'll rename this to aging rate. And then, finally we're going to just multiply that aging rate by the noise values. So multiply. So as before we set this, I'm going to take that aging rate and multiply that with the noise, the absolute value of the noise, and voila, there we go. So and then we're gonna plug that guy and drive the aging rate on the sim as well, the growth simulation. So so here we go. So this is good. So the next step now is going to be to break up the spread itself. The spread right now is just way too soft, and we're not doing any kind of fractal pattern or anything. So let's do that coming up. Okay, so next what we're going to do is spread, create these tendrils. So we're going to use the noise to guide that. So if we change our point scope to visualize the noise again, just to be clear about what we're thinking about doing, we can see here that the low values of the noise would be good candidates for kind of crawling along. So let's how we're going to do that. So the way I'm going to propose doing it is to say, inside of our grow point age part of our solver, right now we're just adding the the weighted or the average contributed value of age. So let's just say, hey, what if we just start adding on top of that? We could just add a lot more age where the noise values are low. So we could just say if so let's get the noise value. So get geo property point noise, and that's an array of floats. So then we could check, if the value is less. So if the noise is less than some threshold, for now we'll just call it like 0.05 or something, maybe 0.1. So if that's the case, then so if it's less than that value, then just add like the aging rate or something, and if not, then don't add anything extra. So if we do this and add that contribution in, and by the way, we're looking at point age, so we need to switch our scope back, so we're looking at the right thing. We need to look at point, wait, did I say point age? We're looking at point noise. We want to look at point age, so let's look at that. So here we go. So we've now added in the low regions. We can see that here. So there we go. So this is starting to be something interesting. Of course, the problem now is that we we've initialized point age basically everywhere, right? So we're looking globally across to see our if for every point basically, no matter what is surrounding neighborhood, what the age values of the surrounding neighborhood are, we're just simply checking if the value is low, and then we're just adding rate. So it doesn't create the spread. So we should try to incorporate that. So one way to do it would be to say, well, what if we instead said, if the neighbor contribution, maybe it doesn't have to be so big. Maybe we can make a threshold value and say, if your neighboring contribution, meaning that you're already spreading, there's already age around you, maybe we can make a low threshold if the noise is low, a threshold value, and then add in more. So basically what we can do is say, okay, so what if we say, what if the neighboring contribution is less than some, some value? Now, the best way to do that is to say, to actually compare it to the noise value there. To say, what if the, if the noise value is low, then the threshold will be low. So we can literally just say, if the, if the neighboring contribution of ages actually, sorry, it's greater. We want to make it easy for that to happen. So if it's greater than the current noise value, then we're going to add in that rate. And the cool thing about doing it this way, it means that some contribution value will have a much greater chance of being greater than a low value than greater than a high value, right? So we're basically using the noise as low value regions to make this conditional more likely to happen, to be true, and therefore more likely to be adding extra age. So let's try that. Hey, look at that. So now we can start seeing some kind of spread. Look at that. So this is the right idea. So again, I can play it back. We can see it spreading along now. These low regions are getting, getting ahead. They're getting, more stuff. The only problem is that they're kind of fat. They're still not super tendrily. So again, to analyze this and come up with a solution, let's keep increasing the resolution of the sphere so that we really can get the fidelity and the detail here to make the right choice. So let's go to much higher, 200 by 200, and I think we should also decrease the size of our point drawing here, 0.01. All right. There we go. That took a while, I'm not sure why. So now that's better. Okay, so the last thing, or the next thing anyway, we want to do here is to say, okay, maybe we want to further control the kind of the width. Like, what if we want to control the width of this, of the how thick or thin these tendrils are going to be? So again, if we look at the, if we visualize the point noise, which is driving this. So let's go back and look at the point noise. Okay, it seems to be a little bit slow. I think it's the point scope that's a bit slow when we have a lot of points, maybe. But here we go. So, we can see these tendrils are pretty thin, but those fracture lines are kind of thick. So what we want to do maybe is to say, okay, so maybe it's not enough to just say, or make the noise value, make a low noise value easier for it to add extra age. Maybe we also, when we're adding that extra age, also allow a control as to what are acceptable noise values. So what we can do is say, instead of saying just add the aging rate for all those low noise values, we could have another check. So we can combine this idea with the idea of having an artist control for fracture thickness. So basically what we're going to say is that if it's less than or equal, so if the noise value itself is less than or equal to this fracture thickness, let's call it fracture thickness. Okay, so I think the JIT compiler is a little bit slow while I'm editing here. I think it's re-evaluating everything. So what I'm going to do actually is I'm going to, hold on, I'm just going to pause the graph compilation altogether. So control dot allows me to pause the evaluation and also the compilation of the graph. And sometimes graphs can get big enough that this is necessary. So, all right. So anyway, so this is the fracture width. So that'll be like the width of the fracture lines. So, so if basically we're saying if the noise value here is quite low, right? Whatever lower or equal to this fracture width, then we can add in the age. So we're going to do another if here. Say only if you're less than that fracture width will we actually add the aging rate. otherwise nothing, and then plug that into the true case here. So let's give that a shot. I'm going to unpause this. All right, we're still looking at the point noise, so I'm going to change this to point age to see the age. All right, here we go. And then, yeah, it's quite slow. Okay, so this is actually a very important and interesting part of our tutorial here. So we're having some issues with the performance. It was quite slow. So I took a look and I realized that what's going on is the get points in radius is set to 2. The radius is 2, which doesn't seem to be a problem. But remember, what we've been doing is increasing the resolution of the sphere quite a bit, right? It's 200 by 200 subdivisions now. So we got a lot of vertices in the same space. We didn't make the sphere bigger, we just added a lot more vertices. And that will, the way that get point in radius is currently implemented, by the way, this is going to get better in future releases. We are working on a fix or an improvement to the algorithm here, but for the moment, if your radius, it's sensitive to big radiuses with lots of points inside, and that can make the performance quite slow. And so as it turns out, this is kind of something where you'd want to control anyway. So the fix I'm going to do here is actually a good one to do, even once we have optimized this one. So so first of all, you know, a sanity check, right? We're basically saying get the points in radius with a radius of 2. Well, how big is that? So if we just make a sphere and set it to be a radius, control its radius to be 2. So our search radius is huge right now. So that's why. So it's clearly wrong. What you really ideally want here, I think, though, is something adaptive, right? Because we don't know, if you really want to make this reusable, it has to work on any geometry you feed it. And that geometry could have very different scales, right? It could be modeled in centimeters or in meters or in inches or God knows what. So you really don't know. So it's better to make this adaptive and make the radius based on the relative distances between the vertices of the original mesh. So if you're getting a mesh with really big distances between the vertices because the mesh's scale is big, then you want that radius to count for that. So a simple way to do this, using the available information we have about this mesh, is to think about that relative, these relative vertex coordinates we were computing in a while back in here. These relative point position relative is actually providing us with the distance values between the face point, the center point of each face, to its neighboring, or to its, so the distance is basically between the middle of a face and the end or the edges of the face, the corners of the face. So that gives us an indication as to how big our search radius should be. We could phrase our search radius as a multiple of those distances, and then no matter what dimensions or scale our input mesh is, we're always going to get a pretty good radius, because we don't want the radius to be too big. We just want it to be, you know, cover maybe 3 or 4 distances of faces to work properly. So so that's what we're going to do. So we're actually going to create a new compound that automatically computes the right radius for us. Let's make a compound for that. So what we're going to do is start off with get geoproperty. So by the way, I'm going to disable execution for a moment. So it's going to be point position relative, and we're going to get that from here, and the type for that thing is float 3, and then let's just take the lengths of those things. So we're just going to grab all the lengths, the magnitudes of all those vectors, and we can use an array bound so we can get the min and max values of all those distances for the whole mesh, and then just divide that by 2. So we take the average, basically. Oops, sorry, we need to add them first. So let's add. Seem to have caps lock on. So add and then divide that by 2. put down the value node. Oops, 2. Okay, so this is going to give us the average distance between the middle of faces and the face corners, and that's a pretty good indicator of the size and scale of the stuff. And then we can just multiply this by some kind of user-defined variable. And so before we do that, I'm just going to select all these guys and Control G to compound them, which, by the way, you can also do create compound, same thing. And call this compute search radius. And then I'm gonna expose that multiplier as an input, and then the gonna output. This is gonna be our actual radius, out radius, and then I'm gonna call this. Let's call it radius, or radius factor. So this is not a radius, this is just a factor of, say, 4. The average distance between basically vertices in the mesh times 4 is going to be our radius. And if we do that and hook that up on this, we should hopefully have solved our performance problem. So one thing we can immediately check is unpause the graph, and look how quickly we got everything back. No whirling or fans running or waiting around. So what did it compute? Let's put a watch point and see. Whoops, sorry. Broke the connection accidentally, and now we're back to waiting because the default values is still 2. So this is what we had before. Remember that what it's doing right now is computing a search radius that's huge, and that's why it's a bit slow. So let's just wait for it to finish computing this with a massive search radius and hook up our connection. All right, so now carefully I will add a watch point, and what are we getting? 0? Oh yeah, because, wait, huh? So, point position relative divided by 2. Okay, so what's happening here? Let's put a watch point. Keep doing this. Watch point. It's not getting the property. That's why. Point position relative. Did I misspell that maybe? So one quick way I can check this is just to put a watch point here and see what we got. Oh, and I understand. This is the points. These are the points, not the geometry. That's why. So we actually want this to come straight from our mesh, right? So remember, we're creating our face points, and they don't have that relative position data on there. So it's the actual disjoint mesh that has it. So that's what we plug in here. And voila, look at that. That's the value. So we had 2, which was slow, and now we're down to a very small value, which is right. And did we break it? Does it still work? Let's see. So yeah, works fine. So that solved our performance problem. So now we'll get back to the fracture width. So I put in, so the thing we were doing is putting in this fracture width in our grow point age. Down here, we're basically checking. So the values that we're attempting to add in these low noise regions, we then do an additional check to see, to further narrow down the valid range. And that really is a way to control the width of it, because if we make the threshold value very small, then we're going to carve out very little, allowed values. So if I put it to 0.01, that's going to be quite skinny, right? And it's not even like, it's barely doing it, so it's too thin. Whereas if I make it big, like 0.3, it will be, a lot kind of wider. So if I make it 0.05, that should give us a pretty good kind of a pattern here. So that is the fracture width here. And we've also now automated the radius searching. So we're getting there. Okay, so let's now switch tracks a bit to focus back on, doing the actual mesh breakup. So we want to break up the mesh according to these ages, these point age property values that we're propagating across the points. So basically, you know, again, these are face points, and we're propagating them around these points. But what we're doing, you know, the reason why we're doing all this is that we want to then have every face. Remember that the face points is the center point around each face. So if we turn on the face display, we can see the, you know, there's actually faces here. So if I rewind, so let's see, it's a little hard to maybe see all this. But yeah, so you can see those. Well, let's make the face points a little smaller. 05. Yeah, something like that. So anyway, so the idea, of course, is that we have these face points, and we're growing this attribute, as we'll see here. There they are. You can see those white points appearing. So here we're growing that attribute, or the point property age, and what we now want to do then is to have that age value begin to break that individual face away from the mesh, and not only that, but have the perhaps have that weight value, or the age value begin to shrink the face, so that as it reaches, you know, 1 or some high value, the face has actually shrunk away altogether and vanished. We also want the point age to drive the amount of kind of vorticity or noise or velocity field we might use to kind of make things look like they're breaking up and floating around in space. So I'd say both kind of the advection or the motion of the points of the faces as well as the scale of them be driven by this weight value. So really at this point, the point age is now going to be used as a weighting value. So a couple of different things to do there. So first of all, we want to drive the mesh faces with the points. So let's go into that. So all the stuff that we just talked about, the ages, all that stuff lives on the points, and then of course the disjoint mesh is the disjoint mesh. Now, what we want to do then in here is let's do the point scale first. So from those points, are we looking up the age anywhere yet? We are not. So let's look up the age. So get geo property. So that would be point age. And I'm just going to set the type right here. So it's a float, and that's it. So let's grab that point age from our points. And then we can just, kind of do a linear map or ramp or something. For this kind of stuff, though, artistic control is always nice. Perhaps we want the, even if the age is, increasing linearly over time, we might still want a nonlinear fall off or some kind of nonlinear ramp to ramp down the size of each face. So I'm going to use an F curve for that. So we're going to use evaluate F curve, where the age gets pumped into the X value, and then we apply this curve to control what happens. So if age is 0, meaning that it's black and nothing should be happening, then we want our scale to be actually 1, right? We want the scale to be identity. We don't want to be messing with it. So I'm going to just switch here to the preset curves and find this inversion, right? So an age value of 0 will map to 1, and then an age value of 1 will map to 0, meaning that the face gets completely squished and is vanished and gone, right? So now I could, of course, change this to be not 1 and line up with some other value. And if I do that, then I would allow aging beyond the point of 1 second or whatever unit we're using. But I'm not going to do that. I think for now I'm going to put this, I'm going to keep it at 1 and position 1 and value 0. And instead I'm going to clamp the age, because I think it's nice to work in normalized values as much as possible. So I'm going to go back to the sim face points and go into the grow point age. And as we are growing our age, remember we're setting our age here after doing this little fancy stuff with the noise value lookups. At the end of the day, we are incrementing our age value here with this add. So I'm going to go ahead and put a clamp down and just clamp it between 0 and 1, simple as that. And So the value gets clamped between 0 and 1, and that's what we're always going to be setting on our age, and that way we don't ever have an age that's beyond 1. After 1 it just stays there. This is kind of, you know, one of those things where that was a choice I made. You might want to do things differently, but that's how I'm going to set this up, at least for this tutorial. So now we know that age will never be greater than 1, and that can be useful in terms of simplicity. So going back here, so we are then saying basically that you know, age of 0 will give us full scale, and as age approaches 1, the face will get tiny. So all right, so let's use that then and pump that right into this loop that's looping over all the faces and transforming them from relative coordinates to world space coordinates, being driven by the center point position that we actually this one that we did earlier. So now we're just going to add a little bit more math in here to, I'm just going to call this scale, I guess. So this would be like face scale. This is a number that's derived, of course, from that curve that we have. So go in here, and then what we're going to do is before we add this relative position, or sorry, before we add the particle point position, the face points, back into to the relative coordinates, I'm going to go ahead and scale. So I'm going to multiply my relative point coordinates with the scale. So first scale down the relative coordinates in kind of face point space, as it were, before we add it to the world space coordinates. So that's it. That's all we need to do, and we should immediately be able to see our faces get tiny as the age value gets big. Let's take a look. So you can see here they're beginning to the age values are getting non-zero. And I'm not sure if I see them getting smaller though. Let's see here. Are we getting scale variance here? Let's see, or invariance, I mean. Let's check it out. So we're definitely getting a lot of 1s. You know, so this is now running quite slow, and that's because I put a watch point inside of a parallel for each loop. It's probably the worst place in the world to put a watch point because it really slows down the performance as it runs. So I'm going to remove that watch point and just put the watch point out here outside the loop instead. Much smarter thing to do, so let's do that. So here we can see our min values climbing, so basically we're still at max 1, but now something happened here. What's going on? Face scale is based on face point age. Oh, I know. I did that same problem I had before where I forgot to turn this into an iteration target. So it was multiplying the entire array of phase scales against, in this case, the current slice. So it was the same problem as if I had not turned this into an iteration target. So let's do that. Iteration target true. So again, we just want to be getting the current value in the phase scale array. So just one value per face out of that array. And that will happen if we have it set as an iteration target. So now, let's see. Yeah, there we go. You can start seeing our faces shrink. Look at that. Very good. That's what we want. So now that age is suddenly driving the scale of the faces. And if I turn off the point display here, so let's just disconnect that for a second, and just so we just take a look at our mesh here, we can start seeing how the mesh is starting to break up. And we should also be able to see kind of patterns forming as we can here. See these, that's like a line. Here we have another pattern forming. Here's another one. So we can kind of start seeing now that type of breakup that we were looking for happening as it propagates. So cool. So onward and forward. Okay, so the other thing we want to do with our point age is to use it not just to drive the shrinking of the faces as the mesh begins to disintegrate, but we also want to drive the actual little particle simulation with noise and the motion of the those faces. So we want to drive that with age 2, so that if age is 0, which means that it, like out here where the values haven't been updated yet, we want the that kind of noise, or the noise vectors and the motion to be 0, static, but where the age starts climbing up, we want them to start moving. So let's go into our sim face points again. Remember, we had disconnected the entire little mini simulation going on here. It was a very simple one, just using curl noise. So let's plug that one back in, but instead of so if I plug that in right now, we'll see, as we saw before, that all of the faces, start moving around. What we actually want is to only move the faces that that have age non-zero. So we literally just use point age as a weight on top of this thing. So so this is actually where originally, when I was going to put together the Ford Euler step compound, I had a little scale here to kind of scale the step. So this is where that comes in. So I'm going to put that in right now because we're going to use it now. So I'll multiply here. I'm just going to call this scale. Rename port scale. Oops, if I could spell. Scale. And then this is going to be a simple float. And then let's do, so get geoproperty on point age. So point age, array of float. So here we go, get that guy, and then use that for the weights. And yeah, so now we should only see the motion happening where the faces are shrinking. Let's see. Yeah, sure enough, you can see these guys are moving around. So as their age increases, they get the full blast of that breakup. So so yeah, there we go. So this is now starting to look, we're starting to understand, how this effect is building up to what we saw at the very beginning. So we basically are very close now to having that working. All right, so just some quick housekeeping. I'm going to turn this little thing here into tag all these compounds here and group them into a compound, because this is actually essentially our simulation or motion part of the sim for the face points. So I'll call this simulate motion or point motion. And of course, the geometry here is just our points, our face points, and so it's just some housekeeping to kind of keep this nice and tidy. We'll do some more things in here a little bit later. Also, in terms of housekeeping, just to keep this graph simple and easy to understand, there's a bunch of setup here: constructing the points, initializing the noise, and then initializing the age, and this whole thing to compute the search radius and storing that. So all of this, I would say, is kind of basically setup or kind of initialization of our face points. So I'm just going to take all of these guys and make them into one compound 2, just again for clean simplification. And we can call this compound initialize face points. How about that? So initialize face points. There we go. So this is basically now starting to look simpler and simpler to use. So we basically have creating the disjoint mesh, initializing the face points from that, and then simulating those face points, doing both the motion part of them and growing the age point property on them, and then driving our mesh faces with those points. Yeah, so getting there. All right, we're doing pretty good. We got our disintegration working, at least the mesh part of it. Things are looking up. So how close are we to having something production ready? The UV coordinates are being preserved as well. Well, not so fast. The other thing that we need to make sure if we're going to really use stuff like this on a real production would be to make sure that we can handle deformation and animation. So what if this sphere, for example, was animated? So let's turn on the sphere, check it out. It's being animated right now. I actually threw a simple animation on top of this. But as you can see, our little disintegration effect is not tracking this animation. And that's because we set everything up on the start frame. So if we go back here, we note that when we initialize our face points, and whose positions later will drive the face positions of the mesh, we initialize them on a start frame, which is frame 1, which is defined here, start frame 1, and then we never really, after that we're just using the feedback on the simulation, and we're not looking at what's happening to the actual input mesh and their vertices anymore. So we got to fix that. So the simplest way, really, at least for this part, for the mesh, shrink, or the mesh extraction and that kind of stuff, is really just to bake these positions that we're animating into the object that we're sending, into the disjoint mesh. So right now we have them separately output as this face point position, which is the face point positions that are computed by that mesh, which is animated. So let's just store them as another geo property in the disjoint mesh. That way we can send it over here directly in a single connection, and then look up what the actual positions ought to be from the animation. And then there's a couple of different things we can do. We could play with velocities, and which would involve going in and updating our simulation, or we can actually simply just do a linear interpolation where we use the age value to interpolate from the simulated positions back to the animated positions, and thereby get kind of a nice blend between the two. And I think that's the simplest thing I'm going to do right here. That would work pretty well. And of course, if you want to, you could also alternatively do it in the simulation using velocities, which is the path to go if you need to get more fancy with your sim. But I think for an effect like this, the right place to start is a simple linear interpolation. So we'll start by going in and adding this geo property, so we can do it all with a single connection. So set geo property. So yeah, here we go, and I'm just going to call this face point position. And here's the trick. These guys are not geoproperty per point. These guys are actually per face, because remember, every face point is the center point of a face. So it would be problematic for us to try to say that this data is living per point. It's really living per face. So that makes me need to change this into face component. That's an important thing to know. But that's fine. So let's grab these guys here and just plug them in. So plug that. So now our face point positions are living on our disjoint mesh, and this guy's red. He's hating life because we just made this auto port disconnected. So I'm going to delete that port, and we're good. Right. So that means that the initialized face points becomes more simple. We don't need to pass a separate point position in anymore. We can just pull it straight out of the mesh that comes through here. I believe it is which one is it? No, the thing called geometry, right? So so this geometry here. So let's just do a get geo property, and I'm going to copy and paste the name of that thing, and it's an array of float threes, because they're positions. And so plug that from geometry, and then plug that data right into wherever that point position is going, which is here. So now we're constructing points by pulling it from that property instead of explicitly passing it on its own through the graph. So I can now delete this extra thing and clean up our graph even more. So that's nice and tidy. And before I do anything else, I just want to make sure I haven't screwed up anything. So I'll go ahead and play back our sim again. And now you can see that thing, that sphere. I'm going to hide that because it's creating artifacts. Let's just take a look here, make sure that we're still getting a nice breakup happening. Nothing, yeah, so that's still working. We haven't broken anything. And so as we get into the more advanced graphs like this, we might want to check every step that we don't do anything silly. So yeah. So next thing is to then use that information here to do a simple linear interpolation. Okay, so let's do this. So we're just going to put down a linear interpolate node here. And then we already have everything we need, I think. Oh no, we need to get that other position, right? So I'm just going to do a copy and paste. Actually, we're just going to copy and paste on this one. And we need to make sure we're copy and pasting from the right. We need this from the disjoint mesh, right? Because that's the one that has this stuff in it. And no, that's the, okay, so this was called point face position. Let me check. I guess I should call it face point because we're supposedly use the first word to indicate the component. So that's actually the right way to do this. So it is a face component property. So, oh yeah, no, I did do that. Face point position. So, so yeah, we'll go back in here and pull out that property. So face point position, and it's going to be a type float3. Right, here we go. So then what we want to do, and this is the position, so this is the simulated position here, and this is the animated position really. So we're basically saying we're going to go from the animated position to the simulated position using point age as our interpolant. So when age is 0, we're getting the animated, and when age is 1, we're getting the purely simulated, and anything other than that is going to be a mix between those two positions, and that's what we're feeding into as our actual particles point position. So if we do that, we should now wonderfully see that this crazy effect we're doing also works when the input geometry is being animated and rotated and deformed, and anything that's really happening, it will work. Look at that. So we can see our nice breakup happening, but it's still being respected. I mean, the animation is still being respected as the effect progresses. So that's pretty cool. Yeah. All right, so that's that. Yeah. All right, so actually one kind of obvious thing that's happening here is that since the animation is moving all the way over here, and the original simulated points were all here, we're getting this stretch happening where by simply interpreting what the simulation gives, which is all going to be stuff over here, from where the animation is, we get this kind of somewhat unnatural stretch happening. So just doing the simple interpolation may actually not be the right thing here, so we're not going to do that. So let's do the simulation part instead. So I'll show you how to do that. So, so let's first off just get rid of this part here and plug this back and get rid of this interpolation business. Although it's still hopefully a useful thing to know about that type of method can be done. So I'm going to actually cut this node because I'm going to reuse this node in the simulation point or compound instead. So let's just do it in here. So in the face points where we actually simulate the motion, we're going to go in here and get that animated position in here instead. So let's do that. Oh wait, hold on. Let me make sure I'm getting. We actually need to, for that to work, we need the actual mesh. So let's plug the mesh in here as well, because it's from the mesh that we're going to be able to pull that property. So we put the mesh through here, and so from the disjoint mesh is where we want to pull that property. And now we can simply create a new velocity here that will counteract that, that will help us solve this. So we'll do subtract from the original, animated position, and then subtract away our simulated position. So this gives us a delta vector, and that can basically be added in as, oh yeah, so we want to weight this. So multiply this this kind of corrective, this is like a corrective vector, or like a little impulse basically. So we're going to weight that by the age, so that if age is 0, we don't we want full correction then. So age is 0, meaning we want, we want that to be, so we need to put an F curve down. So evaluate F curve and then invert that thing. So let's just do this there. So when age is 0, we get weight 1, which is full correction. And as it goes to weight being 1, we don't get any of that correction. We just want the fullest simulated value at that point. So there we go. And that's what we're adding in. Oh yeah, this is now a, let's see. Hold on here. We want to, we want to take the age, plug the age into this, of course. So then, so here we go. So now we are basically multiplying, so we're weighing this corrective vector by the inverted age value. So that is our additional thing to add in here. So let's take, so here we're already computing kind of like this noise velocity. So why don't we just, so it gets a little bit more complicated because we are here. So I think the simplest thing is just to add another forward Euler step here. That would be the simplest. So let's just, so in that case, we don't need this multiply. We can just use this as the scale. And this is our corrective vector, which is really the velocity here. And position is going to be the position output from this. And that's what we plug in. Let's take a look at that. So what we should see here is the mesh move. So yeah, that's working. And you can see as it's breaking up, that seems to be working too. And now we're not getting this long kind of stretchy thing happening anymore, but we're getting these nice velocities and rotational, parts. So obviously the noise is a little bit wild here and there, so that's happening. But now, that's the right thing. And just to double check, if we turn that sphere back on, visibility, we're not quite there. And I know why, because the reason is that our corrective vector right now is the actual full correction for the entire frame. But if we look inside forward Euler step, remember we're multiplying by dt, by the frame length. So we don't want to do that for this. So we're just going to get rid of that. So we want to take, we just want to use that corrective vector for the full time step and not, not multiplying by the time step, but just for the full frame. So, so let's see now if they line up. And that looks pretty good. So we're lined up with animation, but we're still getting our kind of disintegration. Turn off the visibility. So how's that looking? Yeah. Cool. So there is our broken up guy. So that is the better way of doing it, the much better way of doing it. So so now we have this part set up. All right, so the other layer or effect, so the section we're going to do now is on the particles, the kind of the disintegration or smoke particles that we're going to add on top of this. So for that we need to create another particle system, a very simple one, just to kind of create the effect that while the faces are breaking up, the little dust particles are also being broken off here. So the simplest thing here would be to just go in here and grab, copy, paste, really the simulate point motion. Actually, don't know if we need. What we're going to do is copy and paste the switch on start frame. That's really the main thing we're after, that we're going to steal. So let's make a new compound called sim dust particles. And we're obviously going to need to riff off of our phase points for a variety of reasons. We want to sync in many ways with it. We're also going to need, actually, I think that's probably all we need initially. So let's do that. So the basic idea here is to create another simulation compound. So we're going to do, you'll follow the same pattern as before, where we have defined the start frame, and we're going to, we're going to pull on some initial data and then use the simulation data on the other frames. So we don't need to change the internals of this. This is still the same. But the first step in any event is to scatter points, a whole bunch of dust points on this, on whatever the geometry that we're disintegrating happens to be. So in this case, that disjoint mesh is coming from here or here. And I think, to be honest, it's going to give us better results possibly to use the original mesh, not the one that we made disjoint, that we broke up here, but the original. So I'm going to go ahead and plug that in, and I'll call this original mesh. We're going to scatter points on that, so we use the scatter points. This is another Rebel compound in the Rebel pack, but it's quite useful for just quick and dirty scattering of points and things. So let's plug that into the geometry, and let's just go with like, I don't know, 10,000 points to start off with. So number, not a density, is exactly what we want. Very good. And then let's just say, just get started, that's our start frame. On the start frame, basically scatter my points, and on every other frame after that, just use the simulated points. So I'm going to call this sim points or sim dust points. And then we want to do that integration of some kind of noise or whatever. So, for now, again, I'm just going to go and steal that. We already did that here. So I'm just going to steal this forward Euler with the curl noise stuff. So let's just try to match that a bit. So here we go. There we go. And then go back into the sim dust particles and add this little bit here. So now, get the position of our dust points and do some curl noise. Maybe not by 10, let's just do like by, I don't know, by 3 or something. And I think we can also increase the frequency of this noise. So I'm going to actually multiply that position by another value, scale it up value. So let's do it like 10 times that frequency. So here we go. So if you multiply the position of it before you call a noise function, that's the same thing as frequency, as changing the frequency of the noise. So here we go. And then forward Euler step that, whoops. And then we just set point position. And we're done with this, or at least we're done with the first part, the first step here. So, so put that in there, and then we're going to create the feedback to the sim dust points, and I'll call this out dust points. So, and we have to set the types here. So this is going to be a type object. Let's just open up the menu, say object. So that's an object, and that should be set explicitly to be an object, because these are feedback ports here. So they have to be, the types have to be set for feedback ports. And we're not even using this thing yet, but we will. So yeah, let's just take a look at what that looks like. So let's check out these dust particles. I'm going to plug that into the point scope and plug that right in there. And let's just rock and see how this goes. If we're getting any points, maybe I can see which one is the point visualizer. I'm going to hide this. I see 1 point. Okay, something's up here. So let's see. Oh, because the start frame is crazy. I did not put down the start frame. So do we have a start frame here? So at this point, we probably want to do the same thing with start frame as with our aging rate. So we just want to make like kind of like a global value for the start frame. Again, I'm going to change the display mode on this thing to be the name instead of the value and call this start frame. And I'm going to make that 1 so everyone gets the same start frame. So that's the start frame and that's the start frame. And now we kind of have like a controller for that. We can easily control the aging rate and the start frame in one place. Okay, so we got our points, and what's happening here? Are they moving or anything? No, no moving. Let's see. So we initialize, we scatter those points in the first frame, and let's see. And then we actually go ahead and move them on the first frame too, but that's fine. So let's see here. Oh, scale. We did not hook up scale, and scale is 0. That's why. So let's see. For, well, you know what? We're just going to go ahead and do the, well, all right, just to show you, I'll put in 1. So now they're all going to move at once, which is not quite what we want. But hey, look at that. That works. So we have a simple particle thing. But what we really want to do here is the same as we did before. We want to use the point age from the phase points and use that to control how much they're allowed to start moving around. Now here's the kicker. It would be tempting to say, oh, we'll just, you know, get the point age from, you know, from where, right? Well, from here. But remember, these sim points, these the points here that actually have age, those are the phase points, and they are quite different. That's a completely different particle system. Versus the dust points, which are of course also a different particle system. So their point indices are not going to line up. We can't just, you know, get the geoproperty for point age off of this thing, and then, you know, expect those indices to line up with the simulated dust points indices. So we can't do that. So what do? So the simplest thing is to just use the get closest points between those two particle systems, so that what we're basically do is on the first frame, after we've scattered our points, we just say, hey, on this first frame, why don't you guys tell me which particle from the phase points you are closest to, and then we can store that in a little array, and then I can use that to always, for, you know, during the simulation here, look up the closest age, sorry, the point age on the closest point of the phase points, and that's how I can get the age. So it's basically like in other packages, people talk about attribute transfers and that kind of thing. So it's similar to that. We're basically transferring a property from one particle system to another through a nearest point. So let's do that. Get closest points. Actually, we want specifically the closest point. And so after we scatter those points, we're just going to plug, so what we want to do is actually plug the sim points, which is the phase points, into the geometry, because that's what we're looking into. And we're using the scattered positions as as the points we're searching from. And I'm going to turn off cutoff distance, and then we're just going to set property. And so again, this is not a geo property, because the size of this array, whatever, is not being, the frequency isn't per point or per phase or anything like that. It's just a raw data. It's just this array of locations. Although actually, we could do this as a geo property. I just realized, because we are guaranteed that it's going to be the same length as the number of positions. So we could do that actually. So maybe that is not a bad idea. So yeah, fine. So let's just do that. So set geo property. So we'll make it a geo property, and it will be a point property then. So let's store the point indices. So here, array long as data, and we'll call it closest. So basically point closest index. We'll just copy that. And that's what we are setting, and we're setting that on our scattered points object. And that's what we feed into the start frame. So now the start frame is scatter the points, look up the closest point index for those scattered points to the phase points, and then store that as a geo property called point closest index. And now in this simulation loop, we can now easily get a hold of the point age or map the point age to our dust particles and any other property as well, like velocity or whatever. So, yeah, so let's now do a get geo property, and that's going to be this thing, and then this is a long array of long, and let's just do that here. So we're going to get it from here, and then now we can look up the age. So let's do get geo property for age. So this is point age, which is a float, array of floats. And that, of course, we got to look that up from those face points. Oops. So here's the age and the mapping to get the right age. So we're going to do get from array. So the array we're getting from is the point age, and the index we're looking up is an array of indices that maps from our dust particles back to the index on the face points. And that's how we get the age. And that can now be, so with age 0, we would want very little motion, because we really want to be getting the motion at that point from the motion of the animation. But with an age of 1, we would want pure simulation. So we can just drive this directly. And there we go. So if I now play this, we'll see that as the age starts growing in this region, we start getting those kind of crazy and wild particles moving. So we now have a similar situation as we already did with when we're driving the mesh faces. I mean, so we're doing that to our particle sim. So that's good, but what we've lost is the animation. So we need to get the velocity, and so what we did, this is the other reason actually why I decided to go with doing it not with the lerp, but with by computing velocities, a corrective velocity inside here, is because if I then stash that corrective velocity, we can use that in the particle sim if I store it. So here's that corrective velocity that we computed. So I'm going to go ahead and just do a set geo property on this. So that's our corrective velocity data, and I'm going to store that here at the end on our particles. So I'll call this point corrective, or point velocity corrective core. This is the thing that is correcting for the animation. Okay, so let's just hook that up. There we go. So again, this is not really that useful for the first part, but it is useful for this dust particle thing, because now I've got this corrective velocity living here. If I put a watch point here, we can see that it's there. Let me rewind. So we'll go to the start frame. We can see there's that point velocity corrected that we can use now in this dust sim. So we're going to get that, and so get geo property, and it's the corrective velocity, and we're going to go to float 3 on that, and of course that we need to get from those face points. So we're getting it from the face points. And same thing, we need to do a get from array here, because we need to remap this given the dust particle indices. So that's that. So now we have our corrective velocity. And so what we want to do is basically add in the inverse of that, I think, because what we want to do is basically apply that same Euler step that we'd applied in the other particle sim. So here we are. So now we want to do that one. I remember we modified this one so we don't have dt in there, the time step, or the frame length, I mean. So that's the one we want to use. So go in here and use that. So here we go. So this is our corrective velocity, and this is the position coming out of here. And the scale, so now the question is, all right, so if age is 0, then we want to do full corrective. So the scale should be 1 and vice versa. So let's use an F curve again. on this. Oops, not that one. So evaluate F curve. So that again should be driven from age. So evaluate F curve on the age and then invert it. So let's invert that, and that's what we're using for our scale on this corrective velocity. And then we are setting that as our new position. So let's see. So there we go. So now our dust particles are also tracking the animation, but we're still getting some stuff flying off here. And that's what we want. So now we have both, actually. See that I think I hid the mesh. So how is this all looking at this point? So we've got our dust particles, and so we can see that as the mesh is breaking apart, we're getting some dust particles falling out of there. The only thing I would say is that they are maybe moving too fast or something, so maybe what we can do is decrease the amplitude on this thing a bit. Maybe 1. So I'm going to hide the mesh. So, oh, that's the particles, hide the mesh. Oh, there. Okay. So here we go. Yeah, that's a little bit better. So now here's the thing. So so you know, we're now looking at some kind of weird motion here, and I think you know, this is the time at which we have to say, okay, what we actually really want here is not just some stupid you know, random velocities from a curl noise. What we want is maybe more of a fluid type velocity field. So I think you know, it's time to jump into the next step, which is building a simple aero simulation that will generate a velocity field, and then we can just start using that velocity field to push our faces and our dust points around to kind of give it that last sense of you know, realism and control. So that's what we're going to do next. All right, so let's add aerodynamics simulation to help drive the positions around particles. So I'm going to put down a basic aerograph and explode that. Here we go. And then so the other thing too is that when, you know, so there's no way of knowing, of course, in real production if the geometry you're disintegrating is a closed mesh or not. But we need a volume to really generate the air swirls. So without, you know, so I'm not going to get all fancy with trying to fill holes or any of that kind of stuff. That's certainly all doable, but it's going to make our tutorial take a lot longer. So a simple solution would just be to use a nice little compound that I've put together called, I think, box from mesh. Hold on 1 second, I'll find it. So I have this nice little compound called B-box from mesh, which is the bounding box from a mesh. If we can take a quick look, all I'm doing is, given a mesh, I take the point positions, I take the array bounds of them, and I add them and take the half, so basically the average, the midpoint of the bounding box of all the point positions. And that's where what I feed in as our precision for a cube creator. And then I just subtract to get the dimensions for the width and the height, and I plug those into the dimensions of our cube. So I'm really just using a create mesh cube, but I'm deriving the dimensions of that cube and their center position from the bounding box of the points. So we're going to use that to very quickly get a nice volume. A box is always going to be a volume, right? So, or closed mesh, I mean, as our air source. So I'm going to plug that in. And then, of course, the mesh we're disintegrating will be the input to this one. And that will just, you know, be a good thing. We don't need a collider, and get rid of that. Use the aero's default settings for now. Yeah, so let's just take a quick look at that. I'm going to make an output for this, and I'm going to disable the other stuff for now. We just need to make sure we get a simple aero happening here. So let's see, play. So we can see that we're getting a bounding box. If I turn on the sphere visibility, oops, There we go. We can see that we're basically getting smoke, you know, where this thing is. So that's good. And also note that the volume, of course, is traveling. So we're getting smoke as the mesh is traveling. So we also have the animation covered. One thing though is that what we don't really want, for this effect, I think, like a rising plume, upward velocities like that. So I think let's do some quick stuff to the aero sim to turn that off. So no buoyancy in particular. I'll just disable buoyancy altogether actually. So let's take a look at that. Here we go. So now we're not getting any buoyancy, we're just getting some smoke. And again, of course, we're never going to display the smoke. We're not going to be rendering smoke. It's just useful to see the smoke so we can see basically what the air is doing here. We could use a volume scope to take a look at the velocities. But anyway, so let's put in some turbulence or vorticity. So I'll put in some vorticity influence. Let's pump it up a bit. Let's make it like 5, scale 1. And actually, no, keep the scale at 0. And plug that in as an influence. So here we go. So we should start seeing a bit of swirling happening here, and we sure do. That looks like it's swirling quite a bit. So that's fine. That's probably a good starting point for us. So I'm going to just again to kind of keep these things, this graph simple. I'm going to select all this stuff here and Control G, make this into generate velocity field, or velocity volume actually, without putting a volume, which happens to be an aero volume. And that is actually, so this volume is now full of nice velocities that we can use instead of all that curl noise stuff we were doing before. So let's do that right now. So we're gonna first, I think the first thing we can do is just do the dust particles. So I'm gonna plug this volume in as an input to the dust particles. And then this is getting a bit messy now. So let me just quickly clean this up for a second here. So here we go. These guys can be our kind of like initialize compound. So I'll call this initialize dust sim points. All right, and then this stuff here is really just our, well, this is the curl noise stuff we're going to change. So all right, so let's do that first. So we have the curl noise, or sorry, the aero volume. I'm going to call this velocity volume because that's how we're going to use it as a volume for velocities. So then there's the sample volume, which is a great little compound. And we actually, there's two different ones. There's one that's for sampling float values and one that's sampling vector values. So of course a velocity volume is a vector volume. So we're going to do sample volume vector, not the other one. So sampling vector values because velocities are vectors, and this is actually called voxel velocities. So per voxel data in Bifrost always starts with voxel underscore and not point underscore, because that's for point data. So velocity. And so that's what we're going to use instead of all this curl noise stuff. Basically, what are we doing here? Multiplying all this stuff here. So for the forward Euler step here, we're literally just going to plug in what is coming out of that aero sim. And we don't need this other stuff anymore at all. Get rid of that. So that should simplify things as a start. Oops. So let me see if I can clean this up a little bit more. Okay. So yeah, so here we go. So let's take a look at that first of all. So if we now re-enable our display of the dust sim particles, and we can actually kill the display of the smoke because we don't really need that anymore, and hide our sphere. Let's see here. Maybe I was hiding the... Not seeing anything here. What am I doing wrong here? So, silly me. So we're sampling volume, but we did not plug in the positions that we're sampling from. So obviously we need to do that. So we are sampling using the positions of the dust particles, of course. Silly me. All right. Let's see. Here we go. I'm gonna take a look at that, and let's go. So. Okay, so as you can see, we're still getting some crazy shooting here, and I just realized that we actually have a little bug I put into this that I'll fix now. These velocities here don't really correspond to anything proper in our sim, and that's because here we're scaling up our corrective step that we're doing to correct for the animation. We're scaling it not based on the point age, which is coming from the face points, but we really should be doing it from this this mapping we're doing, right? So we forgot to remap. So it's the output of the mapping they get from an array. That's what we should be putting into our evaluate F curve here, because we're using the unmapped ages, which is wrong. So now you'll see a much more correct behavior here from our dust particles. So here's the motion you're seeing now of these dust particles here is coming entirely from that fluid sim that we just did. So what's actually happening here is that we're running a full-on aerodynamics solve in here live and driving that with the velocities, driving the dust sim. So we're actually running two sims daisy chained together here live, which is pretty cool that the performance is good enough to be able to do this without too much trouble. So it's kind of cool. So the other thing too, as we were doing with the faces, is that we probably want to scale these particles down to 0 so they kind of fade out. So let's do that too. We go back into here, and we want to add one last thing, which is basically take the age, the remapped age, which we have here, and apply that to point size. So we're going to do a set geo property. So point size is actually a kind of a understood property, a system property as it were, which controls the drawing size of any point geometry. So quite useful to know about, and if you set that to a value, then it will control the size of the points being rendered. So what we're going to do is when age is 0, we want the maximum size, which could be 1 or whatever, and when age goes big, then you want it to go small. So we can use the same curve that we're using here for the scale. We can reuse that for as the basic number, at least for this point size. Now the problem is that the point size will end up being 1, which is going to be huge. I think anyway, let's see. Actually, the point sizes might be reset by the point scope here. Let's see what's happening. Let me check. Setting point size with these values. I wonder if I just do this. Let me turn this off and just quickly do this. So, not seeing the point sizes change here. 1 second. Okay, so if we just plug our, so first of all, the point scope is going to override the size, so that's why we didn't see that. And then by just plugging the particle straight into the output, it doesn't know the shape type, so the size doesn't work. So anyway, so what we're going to do is do a set point shape compound. So this is kind of our compound for configuring the display properties of point data in Bifrost to the viewport and also to Arnold or other renderers. So if you plug in points here, And we have options like disk or point or sphere or whatever. So I'll just go with disk for now. So if I just do this, as I suspected, we'll see giant points. So these, and the reason why we see giant points is because our point size right now is going to 1, right? If we look here, we're basically, the F curve goes 1 to 0, and 1 is huge because this is world space coordinates. So, so a simple fix would just be to say, hey, let's put down a max, something called like max point size or whatever, and multiply that. So multiply this thing with this max point size, and that's what we use to set the actual point size. And then we can call this, oh wait, oops. Here, this thing is actually its max point size. And so that can be, let's say 0.1 instead. How about that? And then we go back. So that looks better. How about maybe 0.05? All right, 0.01. That looks better. All right, so now we should see those points as they simulate. They're going to shrink based on age and kind of vanish. See? So there they are, kind of drifting off and vanishing. Now, obviously, the last thing is that we're not seeing a lot of stuff here, so I'm going to go ahead and make this just a lot more particles, basically. So let's do that. So let's make it like 500,000. So we can see a lot more points and a lot more detail there happening. So finally, let's marry these things together. So what we're going to do is hook up our mesh. Oh yeah, right. So the other thing is that we want to drive the sim points with, not with velocity. I mean, we want to use that velocity volume to drive these phase points relation too. So let's hook that up too. So I'm going to pause the graph here for a second and bring the volume back in here. And pass it into the motion thing here, and then we're just going to do the same thing we did before. So we're not going to do all this noise stuff anymore. So let's just get rid of all this stuff here, disconnect the velocity, and then compute a velocity from the sampling the volume. So sample volume vector. So we're sampling the aero volume, which again I'll just call velocity volume here. And using the positions of the phase points, and it's called voxel velocity. And hook that up into the velocity here. All right, so let's re-enable the graph, rerun. And we should see that on the phase points, and let's start driving. Let's look at those faces. So now we can see, we should be able to see everything in action here. So those are the faces, and so now it's getting crowded, right? All those points are like basically covering up the entire mesh, which is why we only see gray. So the other thing we'll have to do is we want those points to be slightly underneath the surface of the mesh, so that as the mesh breaks up, those dust points kind of appear. So that is one other thing we need to quickly do in our dust sim particles in the setup here. Go in the setup, in the initialize, and let's just bump them slightly down the negative of the normal of the mesh, right? So let's do that. So let's just do get point position. Here we go, and then get the closest, so get closest point on the mesh we're scattering on. So where's the mesh we're scattering? That's the original mesh. Oops. Original mesh. And using those positions that we scattered. And then we're going to use those locations to sample a property of the normal. So put the locations here. Sample again from the original mesh. And we are sampling point normal, not point position. And the point normal, of course, is a float 3. And that's all we got to do there. And then, let's see, so negate that, right? So we want to move it kind of in the opposite direction of the normal. And then add to our position this negated normal. And actually, we don't want to, so let's use another value here. Let's just bump it by a small amount, and of course that probably should correspond to our size of the max point size thing. So right, sorry, so I'm jumping around here. Where's everything? So this is the max point size, which we have here, and let's bring that in. So max point size goes here. So we have that. So let's use, yeah, so let's basically multiply this negated vector, normal vector, by the max point size, and that would be a good amount to bump the particles. We don't need that. And that's what we're gonna, so we're adding that. So now we're just gonna go and set point position. To the original positions, I mean to the original points. So here we go. So look at that. Now they are all inside. They're gray. They're inside there. If I go to wireframe, we see those. We see it's filled. Okay. So how about that? Let's take a check this out. So now what we should be seeing is the mesh breaking up and points coming out, and also the mesh faces kind of moving as well. So it looks like we're still getting crowded a bit. It could be partly because maybe I didn't bump enough, and partly because maybe I did the bump before I do it after the closest point. So technically maybe I should do it before. So let's just do this. Let's just select this whole thing here. And yeah, select this whole thing and make a compound, call the compound bump points. Inward, and we'll just do that after. So so let's place this right after scatter points. So points goes here. Actually, let me turn off the graph. So points goes here. Original geometry goes where it did, and then the bumped points, we now look up the closest point for that. So let's see, that might be better. Maybe it's better, but we're still seeing a lot of crowding, so so let's bump it more. Let's do something like 2 times that maybe. So, but twice of, so let's do twice of the max point size. I'd say that fixed it. So now we're getting kind of a nice breakup happening here with like these kind of dust particles coming out. You know, it could also just be the viewport rendering actually that makes it look like that. All right, very good. We are now basically we have basically created the setup now that I used to do the original shot. So we have all the elements here. The only thing that I haven't done is if we go into the actual graph that I used on, you know, at the beginning of the video, the tutorial, you can see it's the same kind of thing. We got our velocity field generation, the simulations of the face points, the disintegration of the mesh, and the dust particle sim, and all that stuff. So so one thing I should mention is that to control the rate of the spread, I also added a loop here. So if we go to this fractal growth solver, there's a do while loop here, and if you look at the demo scene, you'll see this, and that will, you know, we'll share this as part of the video. So I created a do while loop that actually runs the entire, you know, age propagation some number of times based on the speed. So the speed parameter that you have here controls the number of the number of steps, and that will make the growth propagation go faster if you choose to use that. But if you have watched this whole tutorial, congratulations, it was a long tutorial, but I think, you know, hopefully it was useful and you learned, you know, mostly how you do this kind of stuff using Bifrost. And I think, you know, if you go in and look at these compounds that are created in this Maya scene here, you should be able to understand it now and be able to take this and work with this as a starting point. Other differences from what we built from scratch here that are kind of subtle and small are just stuff like I'm using, you know, instead of feeding live geometry like a sphere into this, I have a file cache that reads in a Alembic or a Bob file, which is this animated head. So stuff like that. So there's file cache nodes, and I also have made it so that you know, for each stage, like creating the disjoint faces or running the velocity field generation from the aero sim, you can control, you know, read or write. So you can just run these kind of separately and cache them out, and then switch each one to read mode. And then the graph doesn't have to recompute all that stuff all the time. So if you're just twiddling, you know, parameters on the dust and particles or on the mesh disintegration, then you can just have all these other ones in read mode and or pass through. Well, that's going to compute. But if you throw them out to read mode, then these later stages will just compute faster and allow you to iterate faster. So this takes us to the completion of the tutorial, and you know, we'll probably look at other fun tutorials in the future, maybe some that are simpler than this. But again, I feel like there's so much good stuff in the new Bifrost 2.1.0 that I wanted to kind of put it all through into a more comprehensive kind of setup and experiment. So thank you for watching.